We can't calculate what happens in a black hole's singularity. The laws of physics literally break down, but we can calculate what happens on the boundary of an event horizon. As matter falls into the black hole, the event horizon encodes that information. The black hole and the event horizon grow in tandem so that the surface area is the exact right size to contain the information for all of the matter that has ever fallen in since the black hole's inception. All that information could translate to everything that exists in our universe. And believe it or not, the math adds up and solves some long-stewing issues in the process. So say researchers at the Perimeter Institute and the University of Waterloo, who first posed this possibility back in 2014. One big problem with the Big Bang, according to the Perimeter Institute, is that the Big Bang hypothesis has our relatively comprehensible, uniform, and predictable universe arising from the physics-destroying insanity of a singularity. It seems unlikely. The black hole hypothesis is a lot cleaner, if mind-bendingly hard to picture. We might live in a universe within a black hole within a universe within a black hole. It might just be black holes all the way down. During the first trillionth of a second after the Big Bang, the universe expanded incredibly rapidly, faster than the speed of light. Over time, that expansion slowed down. Doesn't that sound a lot like a black hole's event horizon? Is it possible that our universe is the event horizon in some other universe's black hole? When it comes to our understanding of the universe, the 20th century was full of surprises. A little over 100 years ago, we thought that the Milky Way galaxy was home to everything we could see in the sky. We thought the universe was static, unchanging, and possibly eternal, governed by Newton's law of universal gravitation. All of that changed dramatically in the span of a few short years. Einstein's general relativity superseded Newton's gravitation, showing us the relationship between matter and energy and the fabric of spacetime. According to his equations, the universe couldn't be static, but must be changing over time, a fact confirmed with the discovery of the expanding universe. His theory also predicted the existence of black holes, which were later discovered, detected, and even imaged directly. This led to a wild idea, that perhaps our universe was birthed from a black hole. Here's what makes the notion so compelling. The defining feature of a black hole is the existence of an event horizon, a boundary that tells a very different story for an object outside of it versus one inside of it. Outside of a black hole's event horizon, any object will experience its gravitational effects as the space will be curved by the black hole's presence, but it can still escape. If it moves fast enough or accelerates quickly enough in the proper direction, it won't necessarily fall into the black hole, but could break free of its gravitational influence. Once an object crosses over to the other side of the event horizon, however, it's immediately doomed to be subsumed into the black hole's central singularity. Because of how severely the fabric of spacetime is curved inside a black hole, an infalling object will reach the singularity within seconds of crossing the event horizon, growing the black hole's mass in the process. To someone located outside the event horizon, the black hole appears to form, gain mass, and grow over time. What does this have to do with our universe, though? If you were to take all of the known, measurable forms of matter and radiation in the observable universe, you'd have to add up all of the following. Normal matter, made from protons, neutrons, and electrons. Neutrinos, ghostly fundamental particles that rarely interact with normal matter. Dark matter, which dominates the universe's mass but has so far eluded direct detection efforts. Photons, or particles of light, which carry energy from every electromagnetic event throughout cosmic history. And gravitational waves, which get created every time a mass moves and accelerates through the curved fabric of spacetime. At the farthest limits of what our instruments can possibly detect, we can see up to about 46 billion light-years away in all directions. If you add up all the energy from all of these forms throughout the entire observable universe, you can arrive at an equivalent mass for the universe using Einstein's most famous relation, E equals mc2. Then, if you like, you can ask a rather profound question. If the entire universe were compressed into a single point, what would happen? The answer is the same as it would be if you compressed any large enough collection of mass or energy into a single point. It would form a black hole. What's remarkable about Einstein's theory of gravity is that if this collection of mass or energy isn't charged and isn't rotating or spinning, the total amount of mass is the only factor that determines how large the black hole is, what astrophysicists call its Schwarzschild radius. Remarkably, the Schwarzschild radius of a black hole with the mass of all the matter in the observable universe is almost exactly equal to the observed size of the visible universe. That realization, on its own, seems like a remarkable coincidence, raising the question of whether our universe might actually somehow be the interior of a black hole. But that's only the beginning of the story. As we dive deeper, things get even more interesting. As our understanding of the universe has improved and been refined over the past few decades, two new discoveries have rocked the foundations of cosmology. The first was cosmic inflation. Instead of arising from a singularity, it now appears that the universe was set up by a rapid, relentless state of constant, exponential expansion that preceded the hot Big Bang. It's as though there were some sort of field that provided an energy inherent to space itself, causing the universe to inflate, and only when inflation ended did the hot Big Bang begin.